Hello, in this video we're going to talk about the binomial theorem. But before that, let me remind you of the Cauchy integral remainder theorem, and we're going to use this to prove the binomial theorem. Cauchy integral remainder theorem told us that the remainder can be evaluated by an integral. 1 over n factorial integral from x0 to x of fn plus 1 of t times x minus t to the power of n. And this is assuming that f is n plus 1 times differentiable with the n plus first derivative continuous. So the binomial theorem tells us, let me kind of recap what binomial theorem is, the one that you have seen using the Pascal's triangle. It tells us x plus 1 to the power of n is equal to the sum n choose k x to the k y to the power of n minus k. Now, if you look at this one for only one variables, you could just replace one of the x and y by 1, and you would get 1 plus x to the power of n is equal to the sum n choose k x to the power of k equals 0 to n. Now you might ask if we can extend this binomial theorem to exponents that are not integer. So what if I'm looking at x to the power of 1 plus x to the power of root 2, or even just 1 plus x to the power of negative 3? So exponents that are not necessarily positive integers. Can we have something like that? And the answer is in fact yes. If you look at n choose k, the definition of n choose k is n factorial over k factorial n minus k factorial. So clearly, if n is not an integer, you can't really define n factorial. So instead, what we're going to have to do is we're going to write this down as 1, 2, 3 all the way to n. And in the denominator, we'll have k factorial 1 all the way to n minus k. Canceling the common terms, we will get k factorial in the bottom, at the bottom. So I'm going to cancel this term. And on top, I will get n minus 1 all the way to n minus k plus 1. So that's the numerator. Now, this definition allows us to define this binomial coefficient for any n, because then n could be anything. So, and this brings me to the definition 8.6. Given a real number alpha and a non-negative integer n, we define alpha choose n as follows. Alpha choose 0 is 1, alpha choose n is alpha minus 1 all the way to alpha minus n plus 1 over n factorial. So that's exactly the definition that I have at the bottom. Now, what we want to prove today is that the binomial theorem that states 1 plus x to the power of alpha is the sum n from 0 to infinity alpha choose n x to the power of n. And this is true for every real number alpha and every x as long as x is in the open interval from -1 to 1. Okay, so let's go ahead and prove this one. Let's set f of x to be 1 plus x to the power of alpha. First thing is that we note that this function is c infinity. So this function is c infinity on the interval -1 to 1, because 1 plus x is, and x to the power of alpha is also c infinity for x positive. Okay, and this is a composition of these two functions. So now that we know this is c infinity, we can find its Taylor polynomial. So let's find the first few derivatives. The first derivative would be alpha 1 plus x to the power of alpha minus 1. The second derivative would be alpha minus 1 plus x to the power of alpha minus 2, etc. So the claim is we can find the nth derivative of this. So that is fn of that is alpha minus 1, and you have to go n numbers down, so it's alpha minus n plus 1, and then 1 plus x to the power of alpha minus n for all n greater than or equal to 0. So basis step would be f of x is equal to, since n is 0, it's the product of alpha all the way to alpha plus 1. So there's nothing here. So this would be just 1 plus x to the power of alpha, which makes sense. Inductive step. Inductive step is this. Suppose fn of x is equal to alpha all the way to alpha n minus n plus 1, 1 minus 1 plus x to the power of alpha minus n for some n greater than or equal to 0. So then I have to take the derivative of this. So that tells us the n plus first derivative of f is equal to alpha minus 1, alpha minus n plus 1. Take the derivative of that. By power rule, we get 1 minus alpha minus n, 1 plus x to the power of alpha minus n minus 1 as desired. So therefore, we can find out the nth Taylor polynomial. The nth Taylor polynomial of f at 0 is the sum k equals 0 to n fk of 0 over k factorial x to the power of k, which is equal to the sum k equals 0 to n alpha minus 1, alpha minus k plus 1 times 1 plus 0 to the power of alpha minus k, that was the formula for fk, divided by k factorial times x to the k. The first expression, the alpha all the way to alpha minus k plus 1 over k factorial, that is just the alpha choose k. So this is alpha choose k x to the power of k. K equals 0 to n. So by the Cauchy integral remainder theorem, f of x is this sum alpha choose k x to the k, k equals 0 to n, plus 1 over n factorial integral from 0 to x f n plus 1 of t x minus t to the power of n dt. So we need to show, in order to prove that f of x is equal to its Taylor polynomial, Taylor series, we need to show that the limit as n approaches infinity of the remainder is 0. So let's evaluate the remainder. Okay, so let's evaluate the remainder and then we'll show that that is in fact 0. Fn plus 1, I'm going to write it down and then I'll evaluate that. So Fn plus 1 is alpha minus 1 all the way to alpha minus n times 1 plus t to the power of negative n minus 1 times x minus t to the power of n dt. If we go back and look at the formula that we found for Fn, we get exactly that. There's an alpha here that I missed, but otherwise that's fine. So now if you look at this expression, we can rewrite this as the alpha minus 1 all the way to alpha minus n are just constant, so we can take them out. Alpha minus 1, alpha minus n over n factorial, and then integral from 0 to x. I'll rewrite the rest of it as well. X minus t over 1 plus t to the power of n, and then there's a 1 plus t to the power of alpha minus 1 dt. So this is what we get. Now, here, notice that this guy doesn't depend on x. That's why I could take it out. I will have to show this whole thing goes to 0. If you look at we're going to take two cases again, similar to what we did in the example about natural log of 1 plus x that we did last time. So we're going to take a look at that by what we saw in a previous example. So this is like really identical to that. If x is between 0 and 1, and this is excluding 1, x minus t over 1 plus t is greater than or equal to 0, less than or equal to x for all t between 0 and x. And if x is between -1 and 0, then we have the same inequality, except it is -x, not x. Then 0 is less than or equal to t minus x. Here t minus x is positive, so we have this. Therefore, in both cases, t minus x over 1 plus t is going to be less than or equal to absolute value of x. Now, let's look at each case separately and look at the integral and see what happens. So for x greater than or equal to 0 and less than 1, the integral from 0 to x of x minus t over 1 plus t to the power of n, 1 plus t to the power of alpha minus 1 dt is going to be less than or equal to the x minus t over 1 plus t, as we discussed, is less than or equal to x. So we get integral from 0 to x, and we get x to the power of n, and clearly this is greater than or equal to 0 because of the monotonicity, because both x minus t over 1 plus t and 1 plus t are non-negative. And then 1 plus t to the power of alpha minus 1 dt. And in that case, if you look at the remainder would be less than or equal to alpha minus 1 all the way to alpha minus n over n factorial. That one remains the same, so that doesn't change. And then times integral from 0 to x, x to the n. I can take out the x to the n, and the rest is a constant, 1 plus t to the power of alpha minus 1 dt. So note that integral from 0 to x of 1 plus t to the power of alpha minus 1 dt is independent of n. So if we prove that limit of alpha minus 1 alpha minus n over n factorial x to the power of n is 0, then by the comparison lemma, limit of Rn of x would also be 0 as n goes to infinity, as desired. So the key here is to show that this guy goes to 0 as n approaches infinity. Now let's take a look at the case when x is negative. If x is less than 0, greater than -1, then Rn of x, So similar inequalities are going to hold. This is the absolute value of alpha, alpha minus 1, alpha minus n divided by n factorial. The integral would be flipped, so we'll go from x to 0. Instead of going from 0 to x, we'll have to go from x to 0. Then t minus x over 1 plus t is positive, and then 1 plus t to the power of alpha minus 1 is also positive. So I made sure that this expression is positive because I'm taking absolute value. And this is less than or equal to alpha, alpha minus 1, alpha minus n over n factorial, integral from x to 0. This guy is less than or equal to absolute value of x. So that's absolute value of x to the power of n, 1 plus t to the power of alpha minus 1 dt. So if you take that out, we get similar to above. It is enough to show this portion approaches 0. Alpha, alpha minus 1, alpha minus n over n factorial, x to the power of n approaches 0 as n approaches infinity. Okay, so now I have to show this sequence approaches 0. So let's call that Cn, alpha, alpha minus 1, alpha minus n, which is incidentally quite similar to the binomial coefficient. It doesn't really matter though. So first of all, this sequence, if the terms aren't 0, then I can apply the ratio lemma for sequences. So let's take care of the case when the coefficients are 0, at least one of the coefficients is 0. So if for some m, Cm is 0, then either x is 0 or alpha is a non-negative integer. Because either alpha times alpha minus 1 times alpha minus n is 0, or x is 0, or alpha is a non-negative integer. In both cases, Cn would be 0 for every n greater than or equal to n. And thus, limit of Cn is 0 as n approaches infinity. So that's when something in the sequence is 0. Otherwise, we may use the ratio lemma. Okay, so we can use the ratio lemma for sequences. So let's look at Cn plus 1 over Cn. And just to remind you, ratio lemma for sequences told us if absolute value of Cn plus 1 over Cn approaches something less than 1, then Cn approaches 0. And if it approaches something that is more than 1, then Cn would be unbounded and therefore divergent. And it also told us if Cn plus 1 over Cn approaches 1, then the test is inconclusive. So we're going to evaluate this. This is alpha, alpha minus 1, alpha minus n minus 1 divided by n plus 1 factorial. And there was also a factor of x to the power of n plus 1. We have to flip the other one, so we get alpha, alpha minus 1, alpha minus n, x to the power of n at the bottom, and then n factorial on top. So clearly a lot of the terms are going to cancel. On top, you are left with alpha minus n minus 1, and then there's an x. At the bottom, we are left with n plus 1. If we look at this, we can rewrite that as alpha over n. I'm going to divide the numerator and denominator by n, minus 1 over n, 1 plus 1 over n, and then times x. I'm going to put the absolute value since I want to take the limit And this approach is alpha over n approaches 0, 1 over n approaches 0. So this approach is absolute value of x. Now, since absolute value of x is less than 1, Cn converges to 0. Therefore, Rn of x approaches 0 as n goes to infinity. And that's exactly what we wanted to prove. Therefore, f of x is equal to the limit of Pn of x as n approaches infinity, which is exactly the infinite sum, k equals 0 to infinity of n choose k, x to the power of k. And this equality holds for every x between -1 to 1, exclusive. And that brings me to the end of this video. So we'll continue with the topic next time. Very interesting example that we're going to discuss next time. And feel free to subscribe to continue with this course. And I will see you in the next video.